Sure. So today is the last lecture. So I will roughly talk about like the last part. What we are talking about is the GOP part. So I am not an expert in particularly this, but okay, I'll yeah, try my best to get how much I can get out of it. Okay. So the okay. Sorry. Oh, it is not moving. Oh, sorry. Just a second. I am having some trouble in this. Yeah, okay. Yeah. So this is the rough outline. Again, I am taking the F2 gravity because I want to associate with my papers which has been published. So I'll also tell a little bit about the GOP. The first part I am not going to talk about this, and ADM mass we talked about. We'll talk a little bit about volume multiplier, and what's next. We are talking about the current paper we are working, which got a very positive review from a good journal. That's some of the results about the phenomenology what we are working on, not in wormhole particularly, but in Gravastar. That we will talk about. Okay. So again, this is the wormhole. This is the embedding, and this was the history. This is just for people who haven't added been to the past meeting. So I'm just quickly going through it. I mean, if there is indeed somebody who needs a little bit help, so you can let me know. So these are the criteria for the wormhole, and this is the rough motivation for the FQ. Focus on the equation 2. So we are taking a non-metricity tensor. That is that after parallel transport, your length of the vector is increasing. So in the under such a connection, this is the holy trinity of the geometric trinity we talked about. This is the complicated field equation, the 9, which is far more complicated than the Einstein's equation. And now this is the metric we have chosen. Once you choose the metric, you choose the technical T mu nu. You calculate the Q by the prescription which I have given in 8, and superpotential comes from 6 and 7. So after all these calculations, these are the energy conditions, and for the Casimir we did. So I'm not yeah, and these are the field equation. That is the rho, that is the 0 0 component, which is the 19, and 1 1 and 2 2 3 3 are same because the tangential pressure is the same whether you take theta direction or phi direction. This is the equation. Now I will start with the GOP. So most of them I will not tell in details because I will just show some of the papers. So people, I'm not particularly expert in this, but so if somebody is interested, at least can have a starting point. So again, let me just recap the rough idea which we talked in the first lecture. That is that the Heisenberg uncertainty principle is very well known. Del x into del p is h by 2. Now at the x tends to 0, we expect that to be by del p counter. Now in the Schwarzschild solution, as we know, again it's a heuristic argument, del x goes as 2g into del p. So this is, so at r equals to 0 singularity, there is a problem. Now, in order to replace that, I'll very soon show some of the other arguments also. We can see that if we do a quick fixing called del x is h cut by delta p and g into delta p, we can see that there is a quick fixing to this. In a sense that we can now see that, I mean, the commutation relation has to change like this, and in order to make sure the dimension is correct, it should have a dimension of length square. Okay, now what is the phenomenological one? I mean, for a grammar burst, we can see it can be shown that the lambda's bound can be done as well as the gravitational wave that can be done. The most interesting is the Suryadas paper in PRL, where he has explicitly shown that some of the tabletop experiments, like the null result of the tabletop experiment, would show these are the bounds. That what is the bound of the lambda? Remember, it is the length inverse square. So less than 10 to the power 36 means 10 to the power 18 order of magnitudes. Okay, so this is the first idea I would say for the deformed one. This is the gravity's rainbow by Ellis, Mollin and this. So look at what they say. So they said that in inertial frame, we are expecting that the like the Planck energy and this to go to 0 in the limit because it should go faster than the EPL if we want to push it our so-called general relativity further than the Planck length. Then the energy momentum conservation equation is 3. Okay, so again, let me just tell you again what we are trying to do. We are trying to do that there is general relativity. We are assuming the Riemannian geometry still holds or the Lorentzian geometry. we are want to see that whether we can write a renormalization group over the metric coefficient or not. So in a sense that if we take the quantum effects or the Planck scale and assume that there is no, what should I say, non-commutative geometry or the lattice, etc., how far we could put the normal general relativity in the Planck length, assuming that we are allowing the matrix to change. So under these conditions, these are the conservation equation 4 and 5. So we are putting the general relativity as much as we could, except that we are trying to do a renormalization group over the Planck length. Okay, now we can rescale this into R of G as it is given the metric. Okay, and after the rescaling, and this 41 they have calculated. So it's a little bit different calculation, but the final answer is somewhat like this. So you can see that it's almost like a Schwarzschild solution, except that there is a f square in dt square and the g square in dr square. So if you take f and g equals to 1, it is exactly like the Schwarzschild solution, and r square by g square is also there. So this more or less shows that, okay, so if you keep an energy scale, so E is coming with a free energy scale, your even Schwarzschild solution does get modified. Or rather, if you ask an inverse question that I started with the spherical symmetric metric like 36, where I have some specific biasness for F and G, what is the capital F and capital H should be? Remember that it should be very consistent towards the Schwarzschild solution, because we know that in the classical limit the Schwarzschild solution gets recovered. So this is the calculation it can be done. Now, why I am telling this? So, in a sense that we can more or less remember in the heuristic argument, we more or less try to say that what is the quantum effect in the gravity. Now, of course, the full quantum gravity cannot be done. Even the proposed model, like whether you are considering string theory, loop quantum gravity, etc., very rarely have exact results. Like in string theory, I am only know like two results, like the Buffer-Strominger calculation and Ashok-Shen's calculation of the tachyonic field. Okay, so the point is that you are asking a little bit different question, that okay, now if I assume that general relativity is true up to say Planck length, what could be the modification of the metric which we are allowed to do? So this is the gravity's rainbow. Rainbow in a sense that if you know that the renormalization theory, that I mean it is IR and UV it is. So it is something which is in the full spectrum. That is, in the IR range, it should go back to your Schwarzschild solution. In the UV range, it should acquire this type of correction. Okay. Now rest of this, I strictly follow the Sabina Hasselfelder's work. I mean, it is in the Living Review of Relativity. It's an amazing write-up. I mean, there is no doubt about it. So I first start with the Gradamkin. So actually, in the Feynman's book also, if you read the Feynman's gravitation lectures, you can see that, I mean, Feynman also argues that how quantization in gravity could be difficult. So in a sense that if you take a two slit, so I'm not going to this, but I'm just saying what was the roughly Feynman's argument. If you are taking a two slit and you put a mass, so because electrons are massive, they would get deflected. I mean, they would have some deflection due to the mass itself. That means you are completely destroying the fringe. So the problem with the fringe is that you cannot observe or calculate any form of observation. So the very fact that if you put a mass here could potentially destroy the fringe, because due to the mass itself, the electron's path trajectory can be calculated, and if it can be calculated, that means it is a deterministic process, and for the deterministic process, you are expected to fringe to go away. So what it does here is little different. So by the scattering, there is a epsilon energy, and how far we are, and we want to see that by the double slit experiment, if we take the so-called the photons energy as non-linear dispersion, what is the uncertainty principle we get? Okay, so this is the argument under the gravity. So this is the order of magnitude. Remember, this is the order of magnitude calculation. So there is no exact relation to this, which will come later. So L is of the order of this. So del x should be order of sine of epsilon, because the epsilon is the angle, and del x should be of the order of Planck length. And now if you see that x and p relation, it is already showing signature of the non-minimal. So okay, so I do the third one. Okay, so the third one I probably didn't do. So the point is that, okay, it's just a one-line algebra. You can clearly see that from the 10 and 11 itself, we are already getting that del p equals to del x equals to so-called the del p plus some 1 by del p term. Because remember, there is a 1 by m here and there is a g here. Okay, so this is so-called the Gedanken experiment, which more or less shows that even for the ordinary Heisenberg principle itself, we should expect a GOP. So far, we have given three arguments. The first argument is the standard one, the Schwarzschild one. If we want to keep the Schwarzschild metric, we are getting this. The second one is by gravity's rainbow, that if you want to put it like this, your matrix would change such a way that, I mean, the del R and del T would be changed. I mean, this is given in the Smolins paper itself. And the third one is that the normal, even the Heisenberg uncertainty principle does gets modified in the context of so-called the mass. I mean, when the V is given by G omega by R, we can expect that change. Now we are asking a different question that, okay, so far so good. I mean, the hand waving arguments, you can make some principal quantum numbers, also some hand waving arguments. But is there a Schrodinger-like equation that after the solving the equation, we can get this type of relation? The answer is the bosonic string theory itself. So in the bosonic string theory, I am not going to do the Namp'o action. So if you take sigma and t are the t is the so-called the proper time coordinate, and sigma is the string, the loop which is moving through the space and time. So if you know that this, I mean, if you take the Namp'o action, I mean not the Namp'o action because you do the square to do the Polyakov action. So in the Polyakov action, the conformality comes free as a byproduct of the so-called wall sheet invariant, angle invariant of the wall sheet. Even it is true for the general D-Brain's case also. So how do you handle the conformal algebra? You approach the conformal algebra by so-called the Verasoro generator. Now, why Verasoro generator are two kinds, Ln and L prime? This I am not going to do. The point is that in the typical SU2 algebra, like say in the angular momentum, etc., these are so-called the compact group. In the compact group, there is only one kind of, I mean, this is due to Wells theorem. I mean, if you do structure factor and if you do the, I mean, the Cartan classification by the sub-algebra, Wells sub-algebra, you will get only the real part. And the real part you will get because it's something called the Haar measure is finite. So there is always a unitary representation for this. For non-compactive groups like the conformal groups, there is no unitary representation. So unfortunately, there is no always real representation. You have to tally the both L and L part. Okay, now in order to get the, okay, so shockingly enough, string theory doesn't have a so-called H cut. The point is that after doing the dimension analysis, you can identify the L square as the H, I mean in the natural units. So only the so-called the tension of the string is the only fundamental constant in string theory. Just like in the gravity also, there is no G as such. I mean, you identify after the Newtonian that, I mean, the K square equals to 8 pi Gm by C to the power 4. So this is the result you will get even in the so-called the string theory. Yeah, so del x is given in this range, and if you do in the so-called complex coordinate in the conformal geometry, it is always best to do in the complex coordinate, because the point is that in the complex derivative it is always, I mean, the Schwarz derivative is always conformal. So any two-dimensional conformal field theory book or even higher dimensional, everybody does in the complex plane itself. Now you can see what we are looking for. In 80, we are already getting the L squared E. Okay, so it is not, it is 1 because it is written in the natural unit. So, I mean, forget about the H cut. The point is that what we are supposed to get, that is the del x into del P, is roughly, even the commutator, should be of the order of 1 plus some lambda P square, that is the energy. So we can see that for the bosonic string itself, the 80 shows that, I mean, we are indeed getting a structure like 1 plus E. So what does it say? It says that if, for a string theory, even if you take just the bosonic string theory, not the supersymmetric string theory, you can indeed expect that the energy momentum uncertainty principle gets modified by 1 plus some correction term, which is the tension of the string. Okay, now what is the loop quantum gravity? So I'm not going to go details into the loop quantum gravity. Of course, the partial reason is that I do not understand it, but the second reason is that the idea of the loop quantum gravity was that if you take the 3 plus 1 formulation of the GR, you can treat it like the classical field theory in I mean as a conjugate momentum of that. I mean that was the original ADM's paper as we talked about in the previous class. The point is that in that conjugate class, you can define the canonical momentum and the canonical commutation relation, something called the Astacker variable. So in the Astacker variable, you can write the GR as a background independent quantum relation. Okay, so this is the loop quantum gravity. Now, why does the relation like 1 to 2 comes? The point is that what you will get by the so-called doing the path integral or the time integral is so-called the non-holonomic constant. How to handle the non-holonomic constant? There is a mathematical trick called the loop representation of this, and the loop representation gives the so-called the JL, the fundamental spin from every vertex to give this. Okay, so 122 shows the standard the spin form network. I mean, what is the area law? And if you can see that 123, it is we are already getting the area law, which is like the energy scale. I mean, the entropy and area are more or less same. We are getting the correction at the Planck length square. Okay, so this is a very, I mean, celebrated result among the few people who does loop quantum gravity. So Mojumdar and yeah, Ramesh Kohl actually use this to calculate the logarithmic correction to the Hawking black hole entropy formula also. But that is not our focus. Our focus is more or less showing that the energy due to the loop quantum, the discretization of the space and time, it does acquires a extra term of LP Planck length square, which we are also seeing in the string theory also. Okay. So for this, so any questions so far? Okay. So
Not really. It is a
yeah,
very
yeah.
nice introduction. You can move ahead.
Okay, okay, fine. So this is the GOP which we'll add right now. So XI and PJs are the so-called the commutation relation. And remember, we want spherical symmetric solutions to be spherically symmetric, and we want the p square contribution. Remember that we want just the p square contribution as it is given. The x and p should be h square plus p square. Okay, sorry. H square plus p square. So if you can see that due to group theory, if you want that what is the SO3 action which keeps the certain functional form invariant, you can come out with that the 22 is the most general one which can. I mean the PI cannot be because the PI, I mean the group cannot act non-trivially under PI, and the PI PJ is the one, and coefficients has to be the modular square of the p square because otherwise the action of the group would lead to different. Okay, again the KMM paper shows that in the lambda tends to 0, where is our normal Heisenberg uncertainty, we expect that f to go to 1 and g go to 0. Now so far so good, but you can ask a different question that okay, Heisenberg uncertainty principle is very fundamental to the second quantization. So if you remember any electromagnetics or scalar field or Dirac field, always the commutator or the anti-commutator comes up with the IH cut onto Dirac delta or like the normal A Dakar, I mean, whatever you take, the Fourier modes or the normal modes. You can ask that, what about the quantum field theory? Shouldn't quantum field theory gets extra contribution due to such a, how should I say, vague arguments are there? So, or also if the field theory is correct, is it even renormalizable to do it? So this is the K and Magnano's paper. That is the second part. Is you can see that I mean they have been implicitly calculated the Feynman rules for such a energy momentum. They have calculated the Feynman rule, did the first loop correction, and the first loop correction they have shown that both tadpole and fish is indeed ultraviolet set or the renormalized. So in a sense that so you can be assured that if you are doing such a thing, like you are at least not falling into pitfall into so-called the non-renormalizability. Okay, and sorry. And this is something I would thank Parthoda for pointing it out. This is the Wagner's paper. The point is that there is a apparently secondary way of thinking that is that if you write your Hamiltonian as a momentum space Riemannian geometry, that is, it is the momentums are in certain Riemannian geometry, both x and p. And if you get the, I mean, the so-called the nonlinear connection, because remember the commutator has to be changed drastically because your pi and pj are not the standard coming from the standard Cartesian coordinates. So if you take that, you can indeed find the GOP deformed quantum mechanics, where so-called and this GOP deformed quantum mechanics could indeed give to the minimum length square. I mean, we have talked. So in the Sabina's paper also, it is told that how non-commutativity could lead to the gap in general also. So this is one of the paper which I really liked, and thanks for showing this. So yeah, I mean, so in a sense that
So
if you
I would like to I would like to mention a comment that this seems to indicate the non-commutative geometry one can reinterpret it as a byproduct of the curve momentum geometry.
yeah, non-commutative can be given as a curved momentum geometry.
Right.
But what I am interested in the for the GOP, it seems like the non-commutativity implies in GOP, which is given in the Sabina. Now, whether GOP implies the non-commutative or not, that I am not exactly sure. I mean, it seems like it does, but
I think GOP not always connected to the non-commutativity, but I can say that the Lie algebraic non-commutativity in a coordinate
hmm.
can always leads to the GOP. Reverse may
Yeah,
not
yeah,
be
yeah, yeah,
true.
yeah. That is the general proof is given in the yeah, Hasselhoff. So please look it into that. I mean, what yeah, Pathoda has said. So this is explicitly given that if you take the non-commutative, like normal non-commutative, that xi xj is theta ij, you can actually compute the lambda itself. I mean, you can actually compute the so-called the lambda p squared. I mean, the lambda is a function of theta. So this is a this lambda is a function of theta. This is a standard calculation which is given. But you're right that for other way, that is if the GOP is there a signature of non-commutativity? That I am not sure. Also, it doesn't seem like, because this is the bosonic string theory, so there is no Noah-Bossword sector in the supersymmetric string. So even in the bosonic string theory, it seems like there is a GOP, but there is no non-commutativity as such. So it might looks like that GOP directly doesn't imply the non-commutativity as such. Okay, so yeah, now I come into the things which we want to compute. So we want to, I mean, the lecture is about the wormhole. So we want to see that whether can we do about the wormholes and what does the GOP gives us some phenomenology of it. So this is the wave function which one would consider. Remember that this wave function is constructed because we do not have the Schrodinger equation anymore. If we have the Schrodinger equation, we only know that Heisenberg uncertainty principle. This is the standard Griffith exercise. So there is no inherent Schrodinger equation. The best way to do it is to so-called start with yeah, how should I say? Start with the wave function itself and not worry about this wave function come from certain equations or not. Now, for the KMM case, this is their paper. I mean, if you can read it, it's good, because I cannot understand that much of mathematics. But the idea here is the so-called variational principle. There is a way of representation to compute the variation energy of a wave function using the variation method. I mean, those who do so-called the DFT calculation, etc. I mean, that is a very important thing. So what they have done is that, okay, even if we do not know the Heisenberg uncertainty principle, we can expect that this to be a Hilbert space. And for a Hilbert space, the norms and the inner products and norms does make sense. So whether we can minimize this wave function, squeeze it to get some applicable result or not. So using that, I mean, using the Lagrange's undetermined multiplier, they have found for the maximally localized state, F and G's choice could be like this. And the K and omega, remember the K and omega comes from this, the dispersion relation. KR and omega is there. And the completeness relation gets thus modified into so-called this. And as we can see that, okay, now we have constructed a Hilbert space. The completeness relation is given by this, and the F and G, etc., given by this, such that we are satisfying the uncertainty relation. Yeah, so 22 uncertainty relation. Okay, now for the, okay, so for the DGS, I mean, that is the Detorny, Gabriel, and Spindle. DGS, they did a more interesting thing. Unfortunately, it is DGS is little more elaborated than the KMM, in a sense that it is more applicable than the KMM. KMM cannot handle the compact Hilbert space or the compact space. DGS, if you look at the paper, there are two different sections, which is compact and non-compact. But the problem with the DGS method, that is the so-called the localized state, is that it gives a defined answer than the KMM, which is actually in a sense that good. I mean, now we have a so-called the litmus test to check that which would be the more correct way of doing the uncertainty principle in the so-called the functional analysis context. Okay, so what they have used is that, I mean, if you take this, I mean the A as a operators, they are interested in that what is the criteria for the operators to have a eigenvalues like this, arbitrary operators. And they have actually used this as uncertainty. And with this, I mean the L's are the some minimal length scale. They got the dx as a dispersion. Okay, so if you can see, this is, I mean, what you expect in the normal Schrodinger equation, you would expect just the p square and some the Fourier coefficient, because p is the Fourier transform and x is the Fourier or the inverse Fourier transform of the p. Here it shows that it is not just Fourier transform; there is a extra eta which is coming. So this is the showing that even for the wave function context, yeah, like we can yeah, get the dispersion of the x as yeah, like the as a non-trivial thing about for the Fourier. And for the DGS, they have found this f and g as this k and omega, and their completeness relation is like this, and their omega is like this, the total volume. So remember, the Hilbert space means that it is a complete inner product space. So the completeness relation should always be there because of the function analysis result. Okay, now, okay, so far so good. What we can expect out of it? So what we are getting out of it is so-called the energy, so-called the Casimir energies extra correction. We got the KMM and DGS. So as you can see, the lambda 1 and lambda 2 are this. So we maintain a general lambda in the dimensionless quantity such that we can fit it whatever we like. So this is done in the Frasino and Panella's paper, that what is the effect of Casimir energy in the GOP corrected yes, GOP corrected quantum mechanics. Okay, and okay, this is, I am not going to do this. The rho is given by this, so you put the in the 0 0 component from the rho, you get the BR, and the BR you get like this, and you find the BR for both KMM, different lambda and different alpha we have plotted. Uh, okay, and ADM mass we have already discussed, so I am not going to do it, but I am, the reason I plotted is because of this. So now we have a lambda is, and the zeta is given. Yeah, this pi square by 144 alpha, that is when there is no Casimir effect of the shape, the zeta would disappear. So as you can see that ADM mass, if it was a normal Schwarzschild solution, we would expect it to be R0 by 2, because the it is 2 gmm by R. If G is 1, it is R0 by 2. Here, due to the Casimir effect as well as the non-commutativity, that is the lambda appears in the third part in 1 by R cube. So we are getting the I mean for non-commutativity, we are getting some contribution to the ADM mass itself, and as you can see that it is changing from the Schwarzschild. This could be indeed encoded into the deflection angle calculation which we are expecting. Okay, now I'll talk about one thing I didn't talk about. So the point is that how much, say, the Casimir energy one needs to keep opening the throat condition. So this I talked about the previous class about the Roy-Choudhury equation. So this comes from the Roy-Choudhury equation, but little bit. So in the Roy-Choudhury equation, there is the PR and PT, all the null energy conditions are there, right? Now you are asking that why the R is more important. So this is given in the PRL paper by Shankar, Norris Dadichi, and Matt Fisher, that if you take the rho plus PR, that is the only R component NEC, you can indeed show that this is so-called the Clomar mass. I mean, the Clomar integral, if you want to define the mass, charge, and angular momentum in a general covariance way, the best way to do it, if the integration can be done, is so-called the infinity, so-called the space-like infinity you do, and you get this. So the point is that using the Clomar integral, they have argued that rho plus PR, whatever this expression is, I mean, this is for the wormhole, this actually is a quantifier which actually tells that how much so-called the null energy violent or the exotic matter you need. So rho plus PR is the main thing, and this is yeah, again like the from our paper itself, the Ghosh, etc. So as you can see, we have calculated this. It is a little bit bad, but point is that you can always look into our paper to get the final answer is the 88. So we got the IV, the so-called the integral volume, that is the 85 one. We actually got the exact analytic equation. So all these F and other things, etc. So-called F1, etc. are the analytic function itself. So just 1 second, please. Okay, so these are analytic function. So in a sense that it's a good thing because you can actually quantify that how much exotic matter you would need to sustain the wormhole. So this is one thing we have given the plots in the paper. Okay, now I'm not going to go to the junction condition again. So the only reason I brought it here again. So remember that we did the Gauss-Koda type equation. We got the extensive curvature, that is that if surface is embedded in a higher dimension, what would be the curvature, not the Riemann curvature. And we got that for the shell, what is the SAB and P. What we did was the 60 is the first whether the Pathoda has asked in the second lecture that what would be the litmus test of the wormhole or any type of astrophysical objects. So I would say that a thin shell around this wormhole could exert a potential like this, and for a potential like this, yeah, like which we have plotted, we could exactly see that. So for your potential like this, we can see that the so-called the minimum innermost stable circular orbit, the east coast, are disappearing. So if we calculate how far the east coast are disappearing, at least for the various etas, we can at least get a hands on how to do the phenomenology. Okay, now this is all what I have to say, but this is based on only the work which we have published so far. So there is a fortunately fresh paper which I am right now writing the reviewers report, which is quite easy. I mean, in a sense that it is minor revision itself. Hopefully, it would get accepted in somewhat good journal. So I am not showing the paper, but I am just showing some of the snippet of it. So in the non-commutative space, which Shunanda also in others do. So you can, if you want to ask that what is the propagation kernels get corrected by. So this is a standard example that I mean in the non-commutative space, if you do the so-called the yeah, SHM A dagger operator, this 2 theta in the path integral formulation would get corrected by the exponential ones. So I'm not going to do how we used it in the
I just
Gravastar
want
context.
to
So
uh, uh, I just want to inform you regarding this paper. I know this paper regarding this the path integral formulation in non-commutative Moyle space.
yeah,
There's some error. You should look at this the paper very carefully because there is a paper written by Professor Sunandan Gangobadhyay and Professor Scholes who actually pointed out the error in this paper. There are some little bit correction in the propagator which they derive are not exactly same which you are now
yeah.
written in
So
your.
the point is that okay, so this is not something which we have actually used. We have used not.
I understand, but
Yeah,
this
yeah, yeah. No, no, that is
explain
actually good because I didn't know. I know the
correctly.
star product calculation he has done
Yes,
quite
yes.
some time. Yeah,
Basically, they are not defined a consistent position basis to calculate
uh,
the propagator in this particular non-commutative space.
yeah, I'll definitely look into it. Yeah, yeah. So yeah, that's how interesting. But I think that it would be the correction would be of the exponential. I mean, the method might not be correct, but I think the correction would be exponential because the point is that it comes like I mean, at the reasonable limit, we are expected to get the normal Feynman integral. So yeah, I'll probably look into details into it. So the point is that we didn't use it. So let me just tell what we did use. So we used the non-commutativity as a effective energy density, which is an exotic matter which has been shown by many people. I mean, lots of PRDs has been printed because it is somewhat a low-hanging fruit. So this non-commutative energy density we have used in the interior of the gravastar, and for the shell we have taken the stiff matter, and the outer ear we have taken the charge Reisen-Nordstrom and so-called the ABG metric. Yeah, that is the non-linear Maxwell function of the Reisen-Nordstrom and the Bardeen charge Bardeen metric. So this is the so-called the stability. It is taken from that paper itself. You can yeah, see. So hopefully it would be. I mean, okay. I mean, assuming that we do not get further reviews, etc., we can probably put it in the archive in 1 or 2 months. Next, probably 1 month. I mean, if we are lucky. Okay. So I was not supposed to. I was not willing to show it, but fortunately the reviewers' comment came pretty good. So I thought that okay, like at least the paper which we are at least supposed to publish, I mean, at least you can give we can give a little bit of interaction what we are. And this is something we have done in very recent. Like in fact, the final coding we have just now completed. The deflection angle, that is the I is the deflection angle. is actually can be computed. This is a computationally a little challenging for us because like I mean we do not have much of a mentor, but using the Python and little bit of help here and there, we actually evaluate to do the numerical integration over our metric, and we are getting that the deflection angles are like this and for various q. So the idea is that okay, this is not the best of this because there is no weak lensing approximation also the other, but point is that at least the standard deflection angle one can indeed at least test by the so-called event horizon telescope, etc., that what would be the phenomenology of such a non-commutativity gravastar. I mean, the outer ear is, even if you do not believe in gravastar, the outer ear is always the Rising from or other charge. So if there is a charge here. So in a sense that this could indeed show at least like what, how the non-commutativity is affecting the space-time. So this is probably a very simple thing or a difficult thing, depends on your programming choice, but at least we managed to get it. I mean, it's not probably the best of the one, but at least we did it like numerically, because so far I have shown every result which are analytic. So this is the first time we had to handle the infinite integral, we have to handle the asymptotes, etc., etc. So this is our result which we are showing, and this seems like a at least phenomenologically litmus test that how we can you understand the gravastar or the non-commutativity. So hope for this paper to get accepted, and the rest of this is done by the this our GRG paper. Uh, okay, this could have been little better because this got garnered couple of citations when it was in archive itself, but unfortunately the luck is ran out. So it probably at this point has more than 30 citations. So this is the work I have wanted to show. So I'm not going to tell details of it. Okay, and yeah, this is what we have ended, and that's it. So thank you very much for all sticking up to this, and yeah, I done.
Thanks,
So yeah,
Sayantan.
any questions?
It's a very, very nice presentation, and I learned a lot of things from your introductory part of the gap and connection with the loop quantum gravity. It is really interesting. And I will suggest you, I have no more questions. I think there are no other questions. I don't know whether are there any other questions from the audience. If they have other questions, they can raise his hand and unmute yourself.
Okay, so I mean, I am in the Inspire app and Google Scholar also, so you can you like contact me via email or any
Yeah,
other like Facebook, etc. I am also
sure.
your, I mean, like the
It
common
would be
friend.
nice you can if you share your slides to me, and then it would be very helpful to other
Yeah,
people.
yeah, that I have shared all of them. These I will share within like 2 or 3 hours. Yeah.
No, it is almost it is a really good presentation,
Yeah, yeah.
and
So some of them I have to really cut it because the point is that the time constant was really bad, and I am right now in the very tough situation of my life. Because I have to submit my thesis very soon. I have two project pending. So, but
mm,
I decided that okay, at least if I do one thing, at least it would be clear to myself. So that's why I said yes to. And yeah, it is really thanks for giving this opportunity because I think that at least even if I was somewhat sloppy in some of the places, I hope that at least overall people can at least take
no, no, no.
some of the
This
things
is
which you
the
can.
main essential idea is okay. There are no other issues. If someone is really interested, they can contact to you through your email. I think that would be not a problem. Okay, anyway, so we will stop here for today. Thanks, Sayantan. Thanks again
Sure,
to
sure.
you. Okay.
Okay. So yeah, yeah. Yeah, thank you, Patsuda. Also, thank you very much for giving this opportunity. Surely we will hang out later. Also, thanks for this yeah, reference. Also, I mean, this is a really good reference. I mean, the I one. I mean, it's good to you know. Also, I didn't know the subtlety of this. I mean, I do not follow the non-commutative that much because my target was to get the wormhole and the field equation. But yeah, I'll
Understood.
definitely look into it, Ivan. And this Wagner's papers is really interesting because the momentum space Riemannian geometry I at least never encountered. Like I mean,
Actually, it
people
is
can
not quite popular. I think it's a less unknown aspect. Those who are actually working in general relativity, the people are busy with the curved space-time aspect. But
yes,
we are not asking why the momentum geometry is not relevant. Why momentum geometries cannot be curved. Actually, the momentum geometry should be considered when you concern about the quantum theory of gravitations.
hmm. Yes, yes, that is true. Hmm.
Hmm. Okay, very good. In fact, I would like to mention other point also. When we study the gravity in a
Hmm.
language of geometry of space-time, we are always concerned about the manifold. Space-time manifold is the most fundamental,
Yes,
Riemannian manifold.
yeah.
But in my opinion, when you study the quantum theory of gravitation in a different ways, there are various ways to approach this quantum theory of gravitation, but all of the theory mentioned that there exists a minimal length scale or fundamental length scale in terms of gap or commutativity,
Yes.
whatever be the manifestation. But the point is that in this particular context, instead of the manifold, space-time manifold, the entire cotangent bundle, I mean the entire phase space is the fundamental. That is why this paper mentioned that the cotangent bundle is a most important ground to develop quantum theory, or it
Yeah,
rather
but the problem is that, okay, I mean, I understand that cotangent bundle gives the conjugation one, but the point
yeah.
is that, I mean, positions cotangent bundle is momentum if and only if it is a symplectic structure, because you want the Poisson
This is
structure to be preserved.
when you mention about the cotangent bundle itself a manifold with the symplectic structure. That is the
Yeah, yeah,
point.
but
It
for the
was
Riemannian geometry, I mean, there might not
no,
be
not
symplectic
no, no.
structure. For
This is
example,
not
it
a
could be a
Riemannian
five-dimensional
geometry.
manifold.
No, no, no. It is not a Riemannian geometry, because this point is that when you consider the one form, the one form always incorporate the intrinsic symplectic structure in a language of two form. This is the connection between this Riemannian, the non the cotangent bundle and the phase space geometry.
Yeah, yeah, that is fine. But I am saying that if you want to explicitly identify the cotangent bundle as the
Mm.
momentum, as the Newtonian momentum, then you would require the symplectic criteria, which I am not sure if it is. For example, it is known that S4 is not symplectic geometry. I mean, you can do it by
No,
the
no,
fluid
S4,
formula.
S4 is not a symplectic geometry, but you know the S2, the
Yeah,
Keller
yeah, S2,
manifold,
S2 is a symplectic geometry. Only
symplectic,
S2 is,
right?
yeah. But locally, of course, you can always find a symplectic yeah, charts to do that. But the
Mm,
globally, the second criteria of the symplectic, that is the there should be a closed form of that. I mean, yeah, that would be violated. I mean, yeah. But yeah,
mm.
yeah, yeah. You are yeah, right about this. That I mean, in a sense that whether the cotangent bundle, what does it? I think partial reason is that I mean, you cannot find a satisfactory Newtonian formulation or anything like that. I mean, if you write the Einstein's equation, suppose in a cotangent bundle form, what would be
Mm.
the Newtonian equivalent of this? Because the Newton's motion
No,
is written in the
I think
4 pi g square.
in that case, I have another paradigm. Can we? I don't know whether can we visualize the entire phase space as a product space in a locally product space, just like a context of Kaluja-Klein approach. You are considering some manifold with some internal space as a product space. So whether can we consider the phase space as a product space? One part is the corresponding to the phase space, or one part corresponding to the configuration space, other part is corresponding to the momentum space. And can we construct some Einstein-Hilbert action on the phase space, so that the particular case on a particular regime, if we compactify the momentum space, then we can recover the corresponding Einstein equation in configuration space. Do you follow? I just
Yeah,
want to
yeah, I
follow
get it. I get it. So the
strategy
point is
for,
that yeah.
yeah.
Yeah, so I definitely do not know. I mean, it sounds like interesting, but I would say that I mean, if I had to take this a little seriously, how where I would look up, I would probably look with the Astacker variable itself. So in the Astacker variable, what is
Mhm.
the corresponding momentum variable of this? I mean, you probably know that for the Astacker variable, what is the corresponding momentum that is written in the Astacker variable? So one can
Mhm.
probably study with the Astacker variable itself, like how the Astacker variable are so-called the, if it is R4, there is a locally it is R8 because there is a cotangent bundle. The locally it
Then
is
is
a
RA.
tangent
Then
bundle
it's
plus this.
RA.
Yeah, so one can probably study whether in the Astacker variable there is some notion of compactification or the membrane paradigm or something like that. But the only thing I can come up with the momentum related in the Riemannian geometry is the idiom formulation. But idiom formulation doesn't cut it because you cannot commute with anything. You have to go to the Astacker variable. So again, you follow like what I am saying that Astacker variable is, seems like the closest thing to the cotangent bundle of a Riemannian manifold.
That's true. That's true. This seems really interesting. I'd like to know about it very detail. Uh, can you send me
Yeah,
the?
yeah. So I can give you a Loop Quantum Gravity book, which I really like. I mean, it is the Gambinian
Okay,
cooling, and it is
okay,
extremely basic. Like you can give it to undergraduate, etc., and
okay,
everything is done in the very detail. So I can share this book where I learned my Loop Quantum Gravity little bit under Joseph Samuel in
okay,
other.
okay, okay. That would be very
Just remind me in the your WhatsApp. I will tell, and those who the participants also, if you want, I mean, you just drop me the mail. I can send you the PDF. I mean, okay, assuming that you are ethically little bit challenged, I mean, it is fine. I mean, like, okay, it's illegally diluted, but the point is that it is a really good book. So just like in string theory, the Zuinberg book is really good for the undergraduate introduction to string theory. So in the loop quantum gravity, I find the Gambini-Pullin's loop quantum gravity is really good. It's 200 page, but it starts with the basic general relativity and deals with the cosmology and the so-called the black hole correction in a very detailed.
Okay, good. Okay, thank you, Sayantan, for this
Okay.
introduction. Bye bye.
Pleasure. Okay, bye.